For this lesson, we're going to be taking a look at more evaluations of logarithms, making use of our definition of a logarithm being equivalent to an exponential function. If you essentially, it's an inverse equivalency. If I swap the x's and y in an exponential, I get the logarithm. Also worth noting here is that how you write this, whether you write this y equals log base a of x or you write this x equals log base a of y, it doesn't matter so long as you reverse them in both locations. So what we're going to do is we're going to take a look at these problems. We're going to evaluate them using the rules, or using this rule, this fundamental rule in particular. And then we will come up with a general rule that's a bit of a shortcut to save us from having to do that every time. Some of these are really kind of obvious cases. So in this case, let's start with this one. So I'm just going to copy this, put a copy down here at the bottom so that we can keep it visible as we work. And so if I take a look at my original expression, y equals log base 3 of 3 to the 2. And so what I'm going to do is, well, the y equals log base a, so base 3, there's my a value. And my x is going to be this whole thing, 3 to the power 2, that's my x. And y, of course, is still just y. Now I'm going to take this and I'm going to rewrite it in this form. So I'm going to say x actually, you know what? I'm going to go ahead and write that. I'm going to say x equals a to the y. And then my x value is 3 squared. My a value is 3. And my y value is unknown, so it stays y. But 3 to the 2 equals 3 to the y. The 3's are the same, so that tells me that y is equal to 2. I'll do the same thing here. My y value stays y. My a value is equal to 4. And this whole thing is my x value. So if I rewrite that as x equals a to the y, notice this started as y equals log base a. So now when I take the inverse, it's x equals a to the y. My x value is 4 to the 7. My a value is 4, and my y value is the unknown. It stays the same, and we end up with y equals 7. So do you notice a pattern there? Log base 3 of 3 to the 2 just turned into 2. Log base 4 of 4 to the 7 just turned into 7. And what we're actually seeing happen here is a property of the inverses of functions. There's a statement saying that a function and its inverse undo each other. Log base 3 is one function, that's a logarithm to base 3. 3 to the power 2, that's the exponential function with a base 3. So logarithm of 3 and the exponential function 3 to the power, those are inverses of each other. So they undo each other, and the only thing that remains is this exponent. Log to the base 4 and 4 to the power are inverses of each other. The only thing that remains is this 7. So we end up with this general rule, which is that any logarithm of base a, where what we're putting into that logarithm is an exponential function of base a, the end result is simply the exponent itself, which in this case is x. Now we could make use of that property to do this next one. Log base 10 of 1. Is there any way that I can write log base 10? Sorry, log base 10 I'm going to rewrite the same way. But is there any way I can write the number 1? Is there any way I can write the number 1 as a power of 10? 10 to the what is equal to 1? And the answer to that is 10 to the 0. So I'm going to write this as log to the base 10 of 10 to the 0. But log to the base 10 of 10 to the 0, log base 10 and 10 to the power are inverses of each other. And so I can apply this rule. Log base 10 of 10 to the 0 is just going to give me 0. Log base 5, and I've got 1 here. Well, is there a value 5 to the power what is equal to 1? 5 to the power 0 is equal to 1. So that's log base 5 of 5 to the 0, which is simply equal to 0. Now, you may not like the way that I did that, so I'm going to show you a different way to do. I'll choose one of these. I'll choose the one with 5, using this idea of an equivalent expression. I want you to see that we didn't need to use the first rule we developed to come up with this second rule. So another way I could do this is I could start with log base 5 of log base 5 of 1. Now to do this, I really need it to look like one of these. So I'm going to make it look like this one. So I'm going to say that equals y. So my y value, of course, is y. My a value is equal to 5, and my x value is equal to 1. So now I rewrite this. So I get 1 equals a, which is 5, to the power y. But as you can see, we end up where we started, in the sense that the rough work I did over here at the side is the work I end up having to do here, which is I have to ask myself, 5 to what power is equal to 1? And I end up with 5 to the 0 is equal to 1, but that's the same as 5 to the y. And so from here, we end up with y is equal to 0, which is where we ended up previously. And so our general rule, our second general rule we'll develop here, is that log to the base a of 1 is always equal to 0. It doesn't matter what a is. And the reason for that is because anything to the power 0 is equal to 1. This is the exponential rule, which you would have developed in a previous class, in a previous year. This is simply the logarithmic form of this same rule. Okay, now evaluating this one. Now this one's interesting. There's two things we can do. There's an easy way and a more difficult way to do this one. The easy way is if you understand this idea of functions and their inverses. Here I have 2 to the power something. 2 to the power something. Here I have log base 2 of something. These 2 to the power and log base 2, these are inverses. And inverses undo each other. So what that actually means is the answer to this is 2 to the something, log base 2 to the something. All that's going to be left over is x. But what if you don't see that, don't remember it, or what if you just don't like my explanation? What if you don't like this inverses undo each other? Well, my first piece of advice is get comfortable with it, because it's an incredibly useful and powerful technique. But if you don't like that, let's take a look at something using our equivalence expression. Now this is going to be a little bit more difficult to wrap your head around, but it does work. Now I've got 5 to the power something. Now this is awkward because of the x's and y's. So I mentioned when we started this lesson, you can also write this way. X equals log base a of y is equivalent to y equals a to the x. And I'm going to use this alternate form here. So what I'm going to do is I'm going to say equals y. I can't say this equals x because x is up here. I don't know what this is going to work out to be yet. X is already defined in this problem. So now I'm in this form, and so I have to put it into this form. So my y value, it's kind of weird actually, it's still kind of weird. I'm going to write this as the part that goes here is the exponent from over here, but it's not just x this time. What was the exponent from this? The exponent from this was log to the base 5 of x equals, so that's this part right here. So this whole log to the base 5 of x was that part, equals log to the base a, so that's going to be log to the base 5 of the thing that was over here on its own, and that's y, so that's fair enough. That works out just fine. But if we take a look at this, we've got log to the base 5 of x log to the base 5 of y. Well, what does that tell me? That tells me that x must be the same thing as y. And this is, like I told you, this is a somewhat stranger way. It's valid, but that means that this y value is the same as x, which means we can actually replace this y value with the value x. 5 to the log base 5 of x just works out to be equal to x. And we end up with the exact same result that we did over here, which is a function and its inverse undo each other, leaving only the argument, in this case an x, in this case an x. So if we had, for example, if I had 7 to the log base 7 of 13, that is simply equal to 13. Because the 7 to the log and the log base 7 undo each other, leaving just this value. And so as a rule, we end up with this. A base, an exponential exponent with a base of a, raised to the power of a logarithmic function of a base of a, which has an argument of x, just turns into that argument itself. And then the last thing to talk about, what if there's no common base possible? What if we can't apply these rules as we've been looking at them? Because many calculators only have base 10 or base e. Log base 10, which is often just written as log of x, or ln of x, which is the same as log to the base e of x. So what if we don't, it's not one of those two? If we have any generic base, there's a rule that we can use, and the way you do that is you have to take the logarithm of the argument of your independent variable x to the base 10, and you divide that by the logarithm of the base of your original expression to the base 10. Now we're going to derive this later on. We're going to do a lesson on laws of logarithms where we'll actually derive this, but we're just going to make use of it for now when it comes to evaluating these logarithms. So I decided to put in an extra example where I just say something like, what is the log of, let's say, base 7 of log base 7 of 15, which doesn't work out. There's no easy way to do this using any of the rules we've talked about. So we're just going to make use of the rule we just discussed, which is that is the same as the log base 10 of 15 over log base 10 of 7. So notice I changed both of these to logs base 10, and then the numerator, I took the logarithm of my x value here, and in the denominator I took the logarithm of the base of the expression. And so on your calculator, if you figure these out independently, so this is going to be approximate, and most calculators will have at the very least just a log button. So if I take the logarithm of 15, I end up with 1.17609 approximately, and then I take the logarithm of 7 and I end up with 0.8450. Actually, I'm going to have to make that 10. And then when I do the division, I actually don't recommend you use these rounded values. I go back to my calculator and I actually make use of the parentheses that are included, that sort of thing. So I'm going to redo this. I'm going to say the log of 15 divided by, and I use a bracket here, and I say the log of 7 equals, and I end up with 1 point, and I'm just going to go to 2 decimal places. So that's approximately equal to 1.39. Now if you have a calculator that will evaluate this for you, then you can go ahead and find that out for yourself. Or there's another way we can check this. So how can we check this answer? We can use our definition, which is if log to the base 7 of 15 equals 1.39, then that means that 7 to the 1.39 should be equal to 15. And so we check that. We say 7 to the power, and unfamiliar calculator, there we go, to the 1.39 is equal to, and in this case, with my rounding, I ended up with 14.95. So rounded to 2 decimal places, that's how close my approximation is. But that at least tells you that you're pretty confident that you've done things the right way. I believe that's it for this lesson. So really this is just rules of arithmetic for logarithms. And you can see here in your homework, I've even told you which rule you can apply in order to answer some of these easier questions or more basic questions at the beginning.